1, 2. That's it. Okay. Yeah. Cool. Now let's get this machine up with a. It's probably practice. Yeah. People think it's an ad sometimes. One, two. So that's on that there. Okay, cool.
Check whether this is registering to your voice there.
Can you hear me there coming through?
Try again.
Is that coming through?
Looks.
Looks. So if I was Harry and I was speaking to the group, I'd want to be speaking this loud for the group to hear me. Do you get it?
Yep.
All right.
Yep.
So now we're going to.
It was going full bar.
Yeah. So we'll do a little PowerPoint. The physics will start. Physics lecture will start at 6 p.m. Right, so we'll come back to there. So we have
So that's the big picture.
Yeah. Okay, so Google. So I think I'll sign in as myself so it's not confusing. So Roger.Paul.School. Yeah. I'm going to send myself an invite to join the Google Hangout. Do you get me? So invite Roger. Paul. School. At gmail.com. Okay. I always find it strange. It picks up other names really quickly. But it doesn't get yeah. Yes. But then we got block. Allow now. Okay, yeah, It's going to ask us to join it again.
Interesting, because they're all through Google. Google applications.
Let's restart it.
Yep, that looks good. Yep, so good. They can't do it, so we moderate it to prevent Sam. All right, and
Let's block the microphone. And now we
allow screen sharing. Screen sharing. Let's go full screen. So screen sharing. And we go here and run the slide show.
Yep. And then we do this. Right. And then can you log in as you and see if you can find it off our BC Physics on YouTube? Comment. If you're helping Julie tonight, could you please give me a call on 0418 174 393 about the lecture? Full stop. We are testing the YouTube link and would prefer that you came in via the stream rather than direct on the Hangout. Full stop. If you are going to use the Hangout, could you use another Gmail address rather than our BC Physics address? Full stop. New program. Look forward to hearing from you or Julie. Comment. Cheers, Roger. Now, what voice recognition is unbelievable, man.
Now, do you want them to go through here, or do you want them to give them a link?
We can send them a link, but if they Google BC Physics University of Melbourne, do they find it? No? Okay. Okay. Okay, so Paul found it accidentally.
He added something. He added the name of
Harry, Quiney.
I think that was his name.
No.
What's the
Name of my channel?
Yeah, what's the name of your account?
BC Physics, one word. Yeah, but one word. No. Remove University of Melbourne. It won't be. I don't think they'll be up yet.
Okay.
Oh yeah. Wow.
So it's your name.
Yeah.
The name of the lecture.
Right. Wow. So can you connect live now and see what happens? Oh, Max? Max?
Yeah.
So we're on YouTube. So we've got it going. Yeah. So
Oh, that should switch over in a sec.
just wait about 30 seconds and
Switch over. This one's the controller, right?
yep, there we go. Switch to there. Now I'm going to switch back. So we're on this camera. Now I'm going to switch back. Right, so you're actually in front. We're on about 10-second delay there. That's what they're getting. And then it should switch back to the projector.
Where's that pointing? Where's that from now?
That's on the internet, way out on the internet.
Oh,
And
they're
there
on
we
the
go.
internet.
There we go. So that's back to the projector.
Oh, okay.
And so if you've got, so now if I do this, should be able to black out. And Tom, can you just listen carefully if you can hear the voice in there? It's going to end up feeding back.
Yep, it's gone black.
Yep, okay. And then that should be back up. All right.
If we,
Hmm?
was going to say it should feedback completely flat.
Good, that's good. So,
Yeah, so it's a delay
and
of
then-
feedback.
that should come back up. There we go. So good.
Now, where are you? And where's your, oh, you've now set up for them.
No, yes, so.
Oh, here we are here.
Yeah, but this is Wodonga. This is Wodonga.
Yeah.
This is us sending to Wodonga. So here, if we suddenly want to send the vision here, we can send this to Wodonga, and this will arrive in Wodonga about 10 seconds later. Watch here.
Will come up there.
Yeah.
This will come up there.
Yeah. There we go.
And you can put this up onto the screen.
Correct.
Or
Yeah.
is that a
No, we don't need the screen because here's the screen.
Oh, you've got the screen.
There's the screen here.
Oh, that's our screen.
Yeah, that's our screen. It's not big projector. This is a
Okay.
projector.
Okay.
That's on here.
Oh, I see, yes,
Yeah.
there. Yes.
That's better. We finally nailed it.
Now it's going to
Wow. Hang on, how comes that?
That's an interesting feedback.
Ask this. I've got to turn the speaker off on here. Yeah. Because this is listening to the Google,
yeah.
And they get the sound, of course, as well.
So let me just make sure that they're not. Yes, they do. So our microphone is muted. Our screen isn't muted, but our screen's on screen share. That's right. So you should have vision of me now, almost.
Yep.
Except
Your legs.
hang on.
So.
No, that's off there. Yeah, that's right. So if I do this, I know because I can't change because I'm not in control. Yeah. So that's off here. Right. So if Max goes back to there. Yeah. Okay, so this is what they're seeing up there. So this is the vision they'll see. So this is Harry. So that's, yeah. So there's enough room there, and he won't know. So by the time, if he moves to here, I'll adjust the projector accordingly. Yeah. So you can get all the way to here pretty well. Yeah. And if it goes there, I'll just.
Sounds okay. I was just checking that.
Yep,
Sound.
that's cool. All right. Max, have you got your lecture to roll? So we'll roll
What's the
that.
name of the new astronomy?
Christian Reichardt.
Was he giving the next lecture?
I know.
I
I recall you telling me this is what I was going to say. All right. So. Pre-lecture, May 5. Reference to external media have been blocked. I don't know what it is, but I'll see what happens. All right. So, Tom, can you see where the on here, where the the master layout is?
Doesn't really
Yes, it does. I was going to put that the lecture will start at 6. I was going to try to put it at the bottom of all your slides, but it doesn't really matter. We can just play.
I see.
Yeah. So now we're going to broadcast this, but they won't know that. Is that coming through?
Yeah, I was just checking the quality.
Yeah, it'll take a while to settle down on the compression.
No, it's just some reason YouTube was setting it back to low quality.
Yeah. So you can see the delay now.
I see. It takes one thing and then takes n seconds to show
Well, it's
you something, and
compressing
then it jumps to whichever
No, no,
one.
no, it's compressing on delay. So remember,
But it skipped about 6.5.
no, this skip 6 slides.
No, it's
no,
really
it's
far
behind.
So it'll say
It's
next lecture something in it.
30 seconds behind. Here it comes.
So it'll say in next lecture.
It's on delay.
Yeah.
This will appear. There's a truck with the red arrows.
For once they're the same.
But watch, that MG will appear in a sec. So there's
Yeah.
probably an extra one that'll move.
Are they back in sync there? Where are we? Are you on YouTube?
It's not in sync. That's the next one.
Oh yeah, no,
That
it's
was-
no, it's
same
out of sync.
diagram.
Yeah, it's out of sync. Same diagram. You had the same diagram twice. You watch now. The particle table will appear in
I'm
about
watching.
15 seconds.
Yeah.
Oh, I see.
Jeff's face will appear.
Yeah.
And then Rog,
There we go.
there's that. Then Jeff.
So you mean it's storing them?
It's
somewhere?
buffering. Yeah, on the internet, which
So,
allows
but it doesn't do that, of course, with the lecture.
Yes, yeah. Wodonga will be 15 seconds
It
behind.
doesn't matter.
Yep.
If it's buffering the lecture,
Yep.
because someone's talking,
Yep.
then there's a whole section. Either it's going to go on longer than the lecture.
They will finish 15 seconds after.
Oh, it's only 15 seconds, you reckon?
Yeah.
Okay.
Well, you can tell now. So watch. Hewitt. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 seconds.
And that was the next slide.
That was Hewitt. Yeah. It's like a delay loop. That's all. Yeah.
So it's doing what it's supposed to do.
Correct. Because if we broadcast it straight away, then they can't hear it because it'll be all, if a packet drops out and all those types of things. So by putting 10 seconds of delay, it gives computers chances to catch up if they miss something and all those types of things. Yeah.
That's the difference you've made.
Yep. Anyway, so we're good. So perfect, Tom. I reckon we're okay. So if I watch that, that's a YouTube feed, so I know that's alive.
Yeah.
And now, for instance, this is out on the internet there, so we can do this, and this in 15 seconds will change to me. Hi there, and then I'm going to go away, and now I'm going to put it back to this, and then you'll see me appear.
And there you were, how are you doing?
I'll come in a minute. Yeah. And then we'll be back to this. Yeah, that's working. Good. And it's 5:23. We've got plenty of time.
Now you're going to like the person who's there?
No.
Because they've got black faces?
Yeah. It's as
Oh,
good
come
as
on, you said it was going to be good.
it's as good as it gets for now. Come on.
You mean if you're standing behind the lecture theatre, can't you be lit from the front somehow?
How?
With a light?
Which light? We'll put. Which light should we put?
I'll find the light.
I've got a torch. I can hold the torch here.
Oh,
Tom. Yes. I found a better camera. That's the better camera.
Doing,
That was the better camera.
but why was that?
Yeah. So let's actually. I wonder if
Oh,
we
you
can
were using
swap.
it last time.
I wonder if we can swap this mid-flight.
I would say.
I'm gonna swap. I'm gonna swap back to the internal camera, the integrated camera, just for now. Should be right, and I'm going to pull this one out.
Looks like it because that's where the video is coming from.
Yeah, yeah. 1, 2, that's better. Oh, cool. The audio disappeared. The audio is back online.
Back to its default.
Oh, phew. Oh, cool. That's better. I can hear it. Oh. Too much to go fucking right.
Broadcast live.
What have you thought of?
I just said too much to go right with the superlatives in between those two. All right, and that's better now because I can pan this on Harry if we need to.
Luckily, there's anyone watching.
Eh?
Luckily, there's anyone watching.
And that's us.
Yeah, that's us. Put this on.
Yeah. So Tom, can you stand where Harry's going to stand again? And just. Yep.
Now, the people here don't see them. We don't see them. We don't want to see them.
Correct. Yeah. Ideally,
Let's see if you can read the board.
I think that's pretty impossible. So, the only way we can see the board is from this camera, but it's hard to have that
The
camera.
board will be up higher for a start.
Yeah.
Yeah,
We've
I
got
was just
no
thinking in
zoom.
terms of the size of the right.
Yeah, I doubt you can see that. See, if we had a USB extension lead, we could get this a bit closer. I think we'll just stick to this, and we'll just simply accept the fact that
There probably won't be much writing for it.
I don't think so. Yeah.
Can I make a suggestion, even though I'm not technically?
Yeah.
For the board, we had an external light.
Yeah.
Make it easy.
Yeah, too many different camera angles, you get me? We can't switch cameras.
No, but if the light came from here, you won't get reflections from the light, but you will get a brighter board.
Yeah, but I'm saying it's such a wide angle lens that the board only occupies a small amount of the field. See, for instance, I'll show what the board is showing us. So I'll show what they see. Here's what they see. So they see that. Is that me off that camera? I think so. Yeah. Yeah. So they see that, and I don't think it's going to be clear enough. Yeah.
Can we
Yeah, I don't think it'll be clear enough. Anyway, we'll just get better.
bring it slightly right, maybe? It's like the more
Yeah, why don't I put
we can bring it across, yeah, because it's that angle that's hard.
Yeah, that's not a bad angle. How about that, Max?
Once the camera focuses, it's okay.
Yeah.
Why don't you shift that to there?
We can't do that. These things are bolted. We've no longer got control on these things. They're all bolted down. Yeah. We can move that a little bit, but I don't think we can move it too far.
Luckily, all we have. How's that?
That's better. How's that, Max?
And I've just brought this in another 30 centimeters or so.
Yep.
And then you can read that through really well.
Yep. All right.
That's what they're saying.
That's what they're saying. And in fact, I think we can afford to even come back across to here.
Thicker texture might be
Yeah, but I just want to see, as long as Harry sticks roughly to here and
He's
to
got a lot of-
here,
Yeah, he's got a lot of room to move, to be honest.
that's not bad.
You can actually read it this time and see this.
Roger was all. Michael. Good. Listen, we're just testing a feed. Are you on tonight with the guys?
That's clear on the screen.
Do you want to have a look on YouTube? And just on YouTube, search for Tom was at VCE Physics and then Harry Quiney.
BC physics one word,
Yeah.
then one.
Search for VCE Physics, one word, space Harry, space Quiney. Quiney, Q-U-I-N-E-Y.
Can't see the small writing.
Yeah, so it's like it's pretty much only the
Yeah.
biggest.
So you hit on that.
Let's
check the
checking
screen.
sizes. Then.
Yes.
Where do you,
This top one's alright.
There we go.
That one's
you can just,
Right over here, we're on the light side.
I don't think they'll be able to read that.
yeah, so it's pretty much has to be at least.
What's in it?
Have you got a new, is that new?
This one, yeah.
It's a brand new.
Hang on.
The new one.
Just stand by. Michael, I'm just gonna,
That's better.
you just ignore my phone.
That's good.
So this is me now testing 1, 2, 3, 4. This should be coming to you in 15 seconds. That's roughly the delay. So 12 seconds. And then now I'll stop and move back out. I can hear it. Okay, but anyway, hold up. No. That's not the visual. I'm now going to give you, stand by, we'll give you video on the screen. We're not expecting you to read that screen. Okay. So we'll now switch the screen feed for you, and you'll get that in a few seconds. We can actually see what you can see down here too. I saw me just walk off and Tom walk into the field. And there you go, you should have a clear screen now. Really? Yeah. Really, it's crystal clear down here. Yeah. So you see the word lecture, next lecture, May 19th on your feed.
Check settings.
Okay, go to settings and turn the quality up to 360p.
Means it's 144.
Because it's probably set to 144. It's that cog on the bottom right-hand side. Yeah. Was it a 144? All right. Now, if you open up your chat window there, you should be able to see us. You'll see one of my students, Tom Lucas, is logged in. How does he open up the chat window, Tom?
It's right next to it, and you just click on the little bar with the smiley face next to
Click on the bar with the smiley face on the right-hand side.
it, and then you can type and press enter.
Yeah, click in there and send us a message. Still signing in. Oh, we can see you watching. Won't allow you to send a message without being logged in, maybe. Yeah. Can you see the other messages from us? Cover and hide in my or you can't see those. Not yet. We saw you before you dropped out again. Yep. You can't see the. Still not yet. Can you see the? Do you see the roller coaster on your screen or not yet? Okay. For some reason we don't see you watching, but send us a chat message if you can. Correct. Yeah. Or you can do it from your laptop too. You know. And you, okay, cool. I hear you. Okay. Now we're hoping to be able to do the switch between the vision and the slides for you from this end. You get me? Okay, see you back in. We see you back in. That's right. Yep. No, we can't see vision of you, but we can see you looking. You get me? That's what we can. Yeah. Yeah. No, you've dropped that again. Yeah. We're deciding to stream it out rather than have bi-directional. There's no need for us to necessarily see you, but you can, if you want, we can invite you into the Google Hangout. I just wanted to test the YouTube stream because then it's easy for your kids to watch too and everything like that. Right?
Roger.
Just testing with the guys up there. I'm just putting you on speakerphone just for now.
You can find out because people. Oh, excellent.
On a per view basis.
Tom, can you keep chatting to him and just get the text, get the link happening? Yeah.
All right, so I'm here. Oh, there you go. Oh no, that's.
I said hi, Julie. Yes.
So can you see the the chat?
That one?
Please, yes.
Yeah. So I just split the date.
Yep. And below there, there's like a
Right. Let me just check
the standard profile thing of the head in the circle. So the head, upper body, and then in the circle. And if you click on that area next to it, you should just be able to type. I haven't got anything at the moment. I'm just seeing if I
Yeah. It's right, we're done.
I don't have.
What does that look like?
This one.
Yeah, it doesn't make that character. That doesn't matter.
Okay.
The box is approximately.
Oh, yeah. Okay. All right.
It just refuses.
So, which is always, that's why I did ask permission. Well, do you mind if we, who's feeding back, Tom? Is that you or that's us? No, it's us here. 1, 2. That's better.
It should just be, as long as you're logged in and you're on that, it should be.
Okay, back to here. Yeah, so
And you can see Rog there, and now it's just moving the screen. I meant on the actual, I meant on the actual screen that it is, just change it to the lectures.
actually, Tom, I'll send them a special message for them. So we'll just see whether they come up.
Yep, so just that tonight just came up on the screen. And it's been minimized.
Can they see me?
Can you see like part of Roger's hand on the screen? No, okay, so you can see it.
No, hang on. It'll,
I've got that.
but they're on YouTube. They're not on YouTube anymore.
You don't seem to be online, so I don't know whether it's a connection issue.
No, but they were on before because they're still working.
I don't know if it's in and out. Sorry.
But just then log back in Google PC Physics Harry Quiney. Yeah.
So what can you see at the moment?
All right. Harry, this is yours. Oh no, it's Max's. Max's, that's yours.
Oh, yes, it is. Thank you.
Oh, okay. So
No picture?
it seems like there's an extra delay. Okay, you can see our home page. Okay, is Roger walking across the screen now? Just came on. No, okay. So
They might have pressed pause or delayed. Yeah, they've actually paused. That's what they've done.
they're back in time. I know what's happened.
Yeah.
So what's happened is that when you've gone and paused it, you've restarted it, but it's actually restarted in a delay.
Yeah.
So if you go down to the bottom, there's the little bar which takes the time. You're actually like negative 10 seconds or so. I can see just because what you were saying was what I was seeing like 15 seconds ago. So if you zoom that right to the far right, you should be able to. So what I'll do is I'll go in front of the camera now. You should see me in approximately 15 seconds. No, not yet. I'll tell you when I see me come onto the screen. Yep, so we're all done now. Cool. Okay, so yep, your chat. Okay.
Sorry.
Now,
Well, just thinking we can buffering time and stuff. Because we actually have to do so. Send it to America.
I'll just see.
You just have to record it. Well,
Nobody got chat more straight because it dropped out, and that came through to you then. Did you get anything? Okay. Now.
that might be my race, doesn't it? I told them. It's true. Yeah.
Well, that's because it's hard to see, like,
Yeah.
the ceiling's extremely flimsy. You can see this.
Okay. Because I saw it the other day when someone bashed the door. It moved.
Oh, it is a strong freeze.
Yeah.
Anyway, what's your rating on
Yeah, do you have a Google account but not a YouTube account?
Sure.
Yeah, because although they're meant to do it, they used to do it.
Why do we not consider?
There you go, perfect.
Okay.
Yep, I've got it.
Why do we consider the line?
Yeah, so it just, you've got a YouTube account.
Also, why don't we teach fluids,
No worries.
modern, and relativity?
Perfect. And I might, I might just check whether you can read what I'm reading, what I'm writing on the board.
And then maths.
And I'll just check the size, because I'll use it an approximate. So you should see me right in a second.
God, you're dressed up tonight.
And are you there? Yep. And that came up? Yep. Perfect. They're all good? Perfect. Yep. Okay, great.
Tell Michael to,
No worries.
did they get messages up?
Yep, that's all good. All right. Yeah, see you later. Huh? Okay.
Tom, can you just turn the audio down on this, please? Yeah. Where is your audio? Is this it? Maybe that's, is that a, you have to press function on these things?
Do more or less more.
So, okay. Yeah, thanks, Tom. All right, so I'll put Harry back on. Sorry, I'll put Max's back on. Yeah, so because Max only started doing hijack indentation tools in Cup 1. And more than half the solution. So they now feel that we use vectors and hijack, and now they're going to do Cup 1. So it's, I think I actually have to change my mind. So it's like that.
But we are. I think we should continue.
Well,
I think
Yeah, but I suspect alpha listening to that. Did we want to keep the crack lines high, or did we want them to come down?
that's question.
Yeah. So I have to deal with demonstrators. There is no way of demonstrators to run
You must be very well, you just got married and you're starting to get a house and you just buy very close to the school.
Well, I do. But on top of that, I have to deal with these
And vehicle companies, they drive insurance.
Yeah.
I got that light to work, but the problem is it floods the screen.
Doesn't matter, because it's even lots of water.
Yes, I know, but it floods the screen. We'll see. We'll see.
There's not many people. Gives me for changing the page.
Yep, done it. Could be that Max's thing's got automatic things that it just it's your one. Harry's, that's yours. That's good. That's okay. Yeah. Okay, that's cool. All right. So stay here. That was good. Good. Right. So where's the problem with the YouTube channel, that is section sharing. So that's their, they're not shocked. So last time I had back here, it was still we're trying to get Harry to come across to talk to the Xbox, the biomedical, you know, the FPL, XPFL, sorry. Yeah, so Tom's sitting back to the CERN after it's time to work on commissioning these expanding apps and stuff like that. Yeah. Cool.
We really want to sit over there.
So good evening, everyone, and welcome. And I now am very conscious of one thing. We've got the group in Wodonga that we're welcoming, but they're actually going to hear us in 12 seconds because they're on 12-second delay. So in 12 seconds time, they'll all be jumping up and down and sort of welcoming our lecturer for tonight, who is Harry Quiney. And tonight we're going on a journey where in VCE, you know the answer is always C. C is the correct answer. So the question always comes up, is light a wave? A, is light a wave? B, a particle? Or C, both? And I think we might actually hit this in option D today. And option D might be neither or something like that. So, of course, to actually pass the exam, all you have to do is actually choose option C. Most of the time, you'll find that as examiners, we make sure that you are unfairly dealt with, you know, so you actually don't do well. So it's an opportunity to find out from somebody who teaches at a very high level, right, to our, I suppose, 5th and 6th years, and then also studies research, that can pitch at a beautiful level where you as high school students will be able to engage. So without more ado, can we welcome Harry? Harry, thank you for coming because it's a cold night tonight. Yeah, and thank you. All right, there we go. No, but can I ask you a favour? Which side of the lectern would you rather stand at? You'd rather stand on that side, okay. I had to guess, Harry. I had to guess. And I know how much you love cameras. Now I'll just move this and I will just improvise to a way. There we go. Do you mind if I do that?
Apparently not.
Okay, cool. Okay.
Yes, I am Harry Quiney. I'm a theoretical physicist. I work in the School of Physics. Light and electromagnetism is, in fact, my main research area. And so it's a great pleasure and something of a challenge, actually, to try and explain what we know about electricity and magnetism in a simple way, a way which isn't too complicated and too mathematical, but one which actually conveys the truth of light, electricity, and magnetism. Now, I'm sorry for this rogue symbol here, just a Microsoft thing. That's supposed to be approximately equal to. The only maths which will appear in this, and actually you won't really need with the first part, is the idea of the exponential of e to the I theta, which is just a sum of sines and cosines. So waves oscillate, they look like sines and cosines. The square root of -1 appears very frequently in descriptions of electricity and magnetism. That's a symbol that you may or may not have encountered in mathematics, but that doesn't really matter. The cosine of theta in terms of this mystical e to the I theta and e to the minus I theta is simply the sum of e to the I theta and e to the minus I theta upon 2. And if I have a function 1 plus x to the alpha, that's approximately equal to the square root of to 1 plus alpha x if x is a small number of the magnitude less than 1. So they're the only mathematical details that are required. And really, fundamentally, the only thing which is important is to remember that waves look like sines and cosines. They oscillate in space and in time, and that very frequently it's convenient to approximate functions using this, which is the binomial approximation. So to begin at the beginning, Newton argued long ago that shadows cast by sunlight, reflections from smooth surfaces, refraction passing from one material to another, these all provided evidence that light was like a particle, like little bullets. And the way that Newton imagined light was like little bullets bouncing off shiny surfaces or being stopped by materials and casting shadows. He wasn't the only person to think about light at the time. Robert Hooke of Hooke's law, you've probably heard of Hooke's law and the law of elasticity, and the fact that force is minus k times x. Hooke and Newton were fierce rivals. and both Hooke and Newton did investigations or made investigations into the theory of light way back in the latter part of the 17th century. And Newton did a slightly sneaky thing. He just waited for Hooke to die. And then when Hooke was dead, he published his collected works on light, which was called Optics. Newton's research on light was published in 1704, and it promoted a particle view of light, which prevailed for well over 100 years, despite the fact that there was a lot of evidence that light was more complicated than just little bullets. It didn't account for all the optical phenomena which were known at the time. A lot of the physical arguments that Newton promoted weren't in fact corrected. They weren't really supported by any experimental evidence, but he was Newton, right? No one's going to argue with Newton. At roughly the same time, Fermat, who's a famous French mathematician and also a physicist, made major contributions to the theory of numbers and geometry and probability, and also the theory of optics. Fermat is famous these days mainly for Fermat's last theorem. He wrote in a margin of the book that he could prove that x to the n plus y to the n equals z to the n has solutions only for the integers n equals 1 and n equals 2, and had no solutions for numbers greater than that. But the proof was slightly too large to write in the margin of the book. Well, it turns out that it took, well, what's it say, 300 years, 330 years, until Andrew Wiles actually proved Fermat's last theorem, and actually saw Andrew Wiles deliver the proof verbally in the Mathematical Institute in the late 1990s. But in physics, Fermat was also remembered for Fermat's principle of least time. According to Fermat, light travels in straight lines in a homogeneous medium. So they are like bullets, but they travel in straight lines if the material is the same. So it travels in a straight line through light, and a straight line through water, and a straight line through a vacuum. The speed of the travel of light is affected by a property of the medium, the thing that the light is traveling through. And we call that property the refractive index. It's a number greater than or equal to 1. N is equal to 1 for a vacuum. N is greater than 1 for all other materials. It's rather a large number for diamond, which is a material which is one of the largest refractive indices, which is why diamonds sparkle and why they're valued as precious gems. It's also related to the speed through which the light travels, and if n is always greater than 1, then the speed of light traveling through these materials is always less than the speed of light in a vacuum. So speed of light in the vacuum is the fastest thing there is. It's in a song, it must be true. And if the refractive index is greater than 1, then the speed is always less than the speed of light in the vacuum. And if traveling through an inhomogeneous material, that is from going from one material to another, as it would be from going from glass to air, or air to glass, or glass to water, the light takes a path, or seems to take a path, of least time. So it seems to somehow make up its mind to travel from the source to the detector through a number of materials, or a material with a varying refractive index, to minimize the time of its path. And we can see this in this diagram, that if A is the source and B is the place where the light is going, then it will travel in a ray. It will come to this interface, the region between the two media, and then it will be bent, or appear to be bent, at the place where the light goes from one medium into another medium, where it has a speed v1 in the first material and a speed v2 in the second material. And the question is, well, which is the point P? What is the point between A and B, such that the path going from, the path going from A to B goes through this point P, such that A to P to B happens in the least time. Now, if you calculate the speeds, if you know that V1 is C over N1, and you know that V2 is C over N2, then you can show that N1 sine theta 1 is equal to N2 sine theta 2, where theta 1 and theta 2 are these angles marked on the diagram. and that is Snell's law. So Snell's law, which you can regard as just an empirical, experimental, observational law of optics, can also be derived from Fermat's principle, which just tells you that the light takes the shortest path from A to B via T. It's sort of like the Baywatch principle. If this was a lifeguard on the sand, and this was someone drowning out here in the water, what path would the lifeguard take such to get from the lifeguard tower to the place where the person in need of help was? Well, they would travel some way on the sand and some way in the water, and probably the lifeguard can run faster on the sand than he can swim through the water, and so the lifeguard knows to enter the water here. Whereas if the lifeguard decided he was just going to go in a straight line, actually that would take a longer time, because he would have to go from A to this point here, and he'd get there pretty jolly quickly. But then he'd have to swim all of this distance, and swimming is slower than running. It's the same general principle. It's the Baywatch principle. Now, you can go through the maths of this, and you can derive all the principles of optics, all the conventional principles of optics. So, for example, you can make a focusing lens with a refractive index n. So here is the cross-section through my lens. It's made of glass or water or gel or something like that with a refractive index of n. And I require that the time taken for every path shown is a minimal and equal. So I want the path going from F to the surface of the lens, through the lens, and out the other side. I want that to be a minimum, and I want it to be the same time. Now, if it slows down going through the glass, then it will actually take a longer time to go through the glass bits, which are thick, than going through the glass bits, which are very thin. And if I calculate the time it takes to go from any point on this plane in a parallel ray through the glass lens to the point F, the time going from there to there, through the glass, and to F, through that path is exactly the same as the time it takes to go from the lower ray to the tip of the lens and then to F. And that's what we call the focus. The focus is that special point, which if we craft the lens in just the right way, all of the rays of light converge onto a single point. And if X is the thickness of the lens, that is, it's the thickness from the flat side of the lens to the curved side, so that distance there is X, then the formula X, which is the thickness of the lens as a function of R, which is the distance from O to this point here, is given by the simple formula, and that simple formula can be derived from Fermat's principle of least time. The same is true of mirrors. If I want to make a mirror which focuses light, like the Hubble telescope, I would have parallel light coming from a distant star. I want it to bounce off the surface of a reflective mirror, and I want it all to be collected at a focal point F. What shape does this surface of the mirror have to be? Well, from exactly the same consideration, what I want is the time taken to go from the plane A to the surface of the mirror and to the point F is exactly the same for that path as for that path. And if you work out the shape of the lens that actually gives you that property, it turns out that D, which is this line here, the distance from A down to D is exactly the same as the distance from A to the mirror to F. For every vertical path going from A and then bouncing off the mirror and up to F. And that line D has a fancy name, it's called the directrix. And in olden times, people studied in great detail the properties of parabolas and hyperbolas. But the equation of the line that has that property is actually a parabola. So y equals ax squared represents the cross-section of a reflecting lens, which has the property that the light going from A to the mirror and up to S always takes the same time. Fermat's principle in action. That's an essentially particle view of light. Christian Huygens believed correctly that the speed of light is finite, but he had a different view. He conceived of a wave bottle of light that looked rather more like light traveling through water or pressure waves through air. Now, it was a fairly primitive idea, but he was on the right track, and he confined most of his observations to so-called geometrical objects, so reflection and refraction, but not so much the more interesting wave-like phenomena of diffraction and interference, so-called physical optics. Now, this is a potentially tricky bit. The wave model of light. If I have a point and it makes a wave, then what I imagine, it's sort of like you've seen explosions. You know, you imagine spheres emanating from a central point. These spheres, or so-called spherical waves, actually have a relatively simple mathematical description, and it's written on the top of it. The U of r, which is the description of the wave as a function of the distance from the point, has this factor, and I'll explain all of these terms in a moment, minus I over lambda r, where r is the distance from the point to the surface of the wave. E to the ikr just tells you that it's oscillating, it's got sines and cosines, so it's an oscillating function. And lambda is the wavelength, that is the distance between the crests or the troughs of the waves. And k is 2 pi on lambda, that's just called the wave number. So this U of r represents a wave which is exploding upwards from a point, and the formula of that wave is given by that relatively simple formula, and the intensity of the wave, which actually tells you how much energy the wave is carrying, is the square of U of r. And again, the little box means is approximately equal to. The energy is approximately equal to, or varies like 1 over r squared. Light behaves like an inverse square law. So if the intensity of the wave varies as the square of the wave, and you believe in the inverse square law, which we certainly do as an empirically observed fact, then this wave must vary like 1 over r. And that's that 1 over r factor right there. And this is the way of imagining it. Here is my point source. Here is my distance r. Lambda is the distance between two consecutive peaks or troughs of the spherical wave. And then there's some slightly fancy stuff, which I decided to include just so I didn't lie to you. This factor of minus I in the wave just tells you the relationship between the source and the wave. The wave which is produced is minus pi over 2 out of phase with the wave, with the source that produces. So it's the wave which propagates is actually 90 degrees out of phase with the source which is making it. So if you imagine a stick dipping into water, the wave which propagates outwards from the stick dipping into water has a phase relationship which is exactly 90 degrees out of phase from the phase of the stick. And the factor 1 over lambda is there simply so you conserve energy. So in order for this to scale it just the right way, you want it such that the amount of energy which is being propagated outwards, just like an explosive wave, a light wave is in this sense the same. You want the amount of energy to be conserved as the wave gets bigger and bigger and bigger. And all of the energy on a particular radius is just spread more thinly over a larger sphere of a larger surface area. And you require that factor of lambda. So that's the way that light really behaves as a wave. There are point sources and spherical waves which are generated from each of those point sources. Thomas Young really made very substantial contributions to optics in the 19th century and was famous for his Royal Society lectures, the Royal Institution lectures. The Royal Institution lectures were famous public gatherings where the great and the good came to hear the latest in scientific development across the empire. Now, Young said the experiment which I'm about to relate and which I'm about to describe to you may be repeated with the greatest ease. Whenever the sun shines and without any other apparatus which is at hand to everyone. Well, the sun is not currently shining, and so it's a little difficult to reproduce Young's experiment here, but it's easy to describe. And Young was a remarkable person. He was a physicist, a physician, an Egyptologist, a writer, a bit of a bon vivant. He was, the most learned and scholarly man of his generation, and he really put in place experimental optics almost 200 years ago. And this was Young's experiment, and it's critical to understanding the nature of the wave-like nature of light. Imagine that I've got a screen with 2 holes, and each one of these holes makes one of these spherical waves that I've just described in such detail. So there's a spherical wave coming out of this hole, and there's a spherical wave coming out of this hole. So I've got like two spheres of waves, both propagating outwards. And if I produce these waves by shining a light on this surface of the screen with the two pinholes in it, then the phase relationship, or the peaks and the troughs of this spherical wave, will match the peaks and the troughs of this spherical waves, simply because these holes will act like sources, and the phase relationship, or the relationship of the peaks and the troughs, will be the same. And what Young showed, and this is critical, is that in order to work out the energy or the intensity of the wave at any distant point, the thing you have to do is to add the waves and then square them. We've already said that the intensity is the square of the wave, but the question is the square of which wave, or what wave? Is it the square of this wave plus the square of this wave? Or is it this wave plus this wave squared? And it's actually this wave plus that wave squared. The most important thing is this, what we call, in undergraduate lectures, the superposition principle. We add the two waves together and then we square it. We don't square the two waves and add the two intensities. Or, if you like, A plus B squared is not equal to A squared plus B squared. This is some intensities, and this is sum the waves. That's what you do. You sum the waves and then you square them. It's the most pervasive principle of modern physics, the superposition principle. It pervades optics, it pervades quantum mechanics, ultimately it pervades quantum field theory, it pervades all of modern physics. It's about everything. A glamorous assistant.
I was going to say next time, can you use that board, please?
Well, I'm a bit photophobic as well.
I know that. That's why there's no monitor there.
Right. Now, Young's experiment, if you actually look very closely at these spherical waves, you can divide it into two pieces, very, very far from the source. You can imagine that as the spheres get bigger and bigger and bigger, if you look at two successive peaks or two successive troughs of the wave which is produced, and you just focus on a cone coming up from the source, what you're going to see is going to look just like a normal wave train, just a series of parallel waves propagating in a particular direction. And then if you look perpendicular to that direction, you're actually going to cut through a sphere. So what I have now, which board do you want me to use?
No, that one there.
This one here.
Yeah, perfect. Thanks, Ray.
Imagine that I've got a cone in the sphere. And here are three crests of the wave. If I look here, then it kind of looks like three parallel crests. That's this first term, e to the ikz. That's the formula for three parallel crests going a long way away. And the second term is what happens if I take into account the fact that the wave is curved and I cut through it. If I just make a cut directly through vertically downwards, you can see that I'm going to cut through the wave in two places like this. And in cross-section, that cut will look like that. It's like cutting through an onion. If you can imagine an onion, you just slice through the onion, then at the very top you're going to see a big ring, then the rings will get closer and closer and closer as you chop your way through the onion. And that is the cross-section of the onion. So this second term is the cross-section of the onion. The e to the ikz is the fact that very far away it looks like a waterway, like some hill beach, a series of crests just propagating towards the sea. I still have this factor of minus I over lambda z. And when I square it, this thing behaves like 1 over lambda z squared. It's again the inverse square law. The amount of energy contained within this cone actually behaves like the inverse square law. So the farther away I go, the fainter or the less bright it becomes. So we can understand spherical waves propagating from sources. We can understand what they look like a very long way away from the source. You can imagine cutting through these spheres like slicing through an onion, and you can see the layers, and those layers are the peaks and troughs of your wave. And you can also see that as you propagate forward, it'll look sort of like a water wave, a series of almost parallel lines, parallel peaks going off to infinity. And again, the square mean is approximately equal to I of x, which is the intensity as a function of x. If you square that wave, it behaves like 1 over z squared, the inverse squared law, and the square of that factor turns out to be cosine squared of this slightly complicated thing. It depends on d, which is the distance between the two point sources. It depends on x, which is the distance from the middle between the 2 point sources, and inversely is lambda z. And if you plot that as a graph, it looks like that. It looks like a series of bright and dark spots or fringes, and it's dark when x times d over lambda z is an odd multiple of pi over 2, and it's bright when it's an even multiple of pi. And so the maths tells us that what we expect to see, and what we do indeed see in experiment, is that if I have 2 point sources and I allow the waves to interfere, I sum the waves and square them, then what I'm going to see is a series of bright and dark fringes, and that's an evidence of the wave-like behavior of light. You see exactly the same thing with water waves, waves and any other material. It's a fundamental property of wave-like phenomena. Now, of course, by about early part of the 19th century, early to middle part of the 19th century, there was a kind of competition between the particle theory and the wave theory. And it was a sort of, it was quite bitter, actually. And the French Academy opened a competition for French nationals and French scientists to really resolve this whole question about the particle wave nature of light. Now, Fresnel, he wasn't a rich man, he wasn't a nobleman, he was a comparative nobody, but formerly a mathematician. Fresnel entered a competition held in 1818 where he developed a Hoyle's spherical wave model and applied it in general to real experiments that could be performed at least in principle. And it was laughed at. I mean, the panel, which was led by Poisson, who was both French nobility and a very, very distinguished mathematician and theoretician, he said it was just a load of rubbish. But some people came to Fresnel's defense, and in particular, Dominique Arage also thought, well, we should give this a go. Arage became president of the French Republic in 1835, I think. He was an extremely influential person. He was the president of the French Academy. And so he said, well, let's do the experiment. Let's find out what's true and what's not true. Is Fresnel's theory right? Well, Fresnel won. It turns out that Fresnel's theory about how light behaves was vindicated experimentally because he proposed the following test experiment, an experiment whose results are so surprising that it just had to be right. Imagine you have a circular coin, something like a coin, an obstacle, and you shine the light all around it. So the light is shining on the coin. In the particle theory, theory says that the light shouldn't get past the coin. It should just cast a shadow. And everyone says, well, it's obvious. You know, if you get a coin, you shine some light on it, it'll cast a shadow. It'll cast a round shadow on the wall. And that's all you're ever going to see. According to Fresnel's theory, though, Fresnel said at every point on this plane, every point on the plane that goes through the coin is a spherical wave. And so every point is producing one of these spherical waves, but there are no spherical waves where the coin is. So right at the corner, at the top and the bottom corner, there's a wave which is propagating outwards, but slightly down from the top and slightly up from the bottom. There's no wave at all. And so Fresnel said, well, funny things are going to happen when I come to sum up all those waves and square them. And according to Fresnel, what should happen is that you can see from the diagram, these waves start to curl around and start to invade the space behind the point. So because it's spherical waves, the light starts to propagate in the region behind the point. And there's constructive and destructive interference. I add up all those spherical waves and then square them. And according to Fresnel, the intensity of the light in a line directly from the center of the coin outwards, which I've marked there as Z, ought to behave like this formula, that the intensity I of Z along that axis should behave like I naught, which is the intensity of the light on the left-hand side of the coin, multiplied by this factor Z squared over Z squared plus A squared, where Z is the distance from there outwards, and A is the distance from the center to the edge of the coin. Now you can see when Z is equal to 0, this is equal to 0. So unsurprisingly, it seems pretty fair that you would not expect to see any light at all, right at that point there where my laser pointer is shining. No light at all. And in fact, that's true. But as you go further along this axis, when Z becomes very much bigger than A, then this number approaches 1. And so what you expect to see is that there should be a bright spot somewhere out here whose intensity is exactly the same as the intensity of light over here. And they did the experiments. They very carefully set up light impinging on a very small coin and total darkness and under careful conditions, and they measured the intensity photographically. This is a simulation, but this is what you see. What you see is that, sure enough, right in the center, I of Z produces this tiny little white spot here. All of this is the sort of classical shadow. You can see that it's dark, but it's not actually black. Some light curls around the edges, and you can see, if you look really closely, that there are some of these lighter bands inside the ridge, and then you get a very bright ring, which is caused by constructive interference of all the waves curling around the coin, and then you see these rings propagating all the way outwards. And this is exactly what you see if you perform the experiment. Fresnel was right. Roger.
Harry, you answered one of the questions I've always wanted to know. I mean, they use photographic plate then,
Yeah, right.
And you, in Harry Quiney's sense, always call it Arago spot rather than Poisson spot, like we do. What light source did they use? Do you know?
It was the sun.
There's a sun.
It was the sun.
Yeah, I figured.
It was the sun dark through it. It was a very
cathedral.
very tall building.
Yeah.
It was probably a church.
Yeah, I was thinking.
A very tall.
Just question about Fresnel zone plates. The similar principle, the way I suppose use the inverse.
Essentially, Fresnel zone plate is a series of apertures. It's the exact reverse. It turns out that instead of having a coin, if you have a hole, an aperture, then you get the same general pattern. But a Fresnel zone plate is just a series of apertures, rings and apertures, so annuli, concentric with one another, where the widths of the annuli are chosen in such a way to actually get constructive interference at particular points along that direction, along the Z direction.
The space between the rings.
That's right, and essentially it's calculated such that those very bright spots appear in different orders. Effectively, what you'd look at is the light and dark spots of the biggest one. The biggest one actually defines the resolution of the zone plate. And then you choose all of the blackouts, the annuli, in such a way to reinforce the constructive interference at different points along that axis. And so there's negative and positive indices of the Fresnel zone plate, and it's all based on the spot varieties.
Did Fresnel think up that idea of the composite?
That came later. The zone plate was the Fresnel zone plate and the Fresnel lens. Fresnel did invent the Fresnel lens. I don't think he invented the zone plate. The Fresnel lens was invented for lighthouses. The focusing lens. From wave optics, we already know that from a distance f from a point source, this wave behaves like that factor which I put on the board. This is the factor that corresponds to the unknown. This is the mathematical equation for the slice through the atom. It's that factor there. And a lens, which we've also already worked out, changes a spherical wave in a plane by an amount which is given by that factor there, which you can see is just the same factor except for the minus sign in the argument. And if I multiply those two factors together, I get 1. That's the important bit of maths you need to know. And so a change in phase delta phi, passing through a thickness x of a material with a refractive index n, is therefore given by this formula, that delta phi is n minus 1 k times x, and that gives, as before, exactly the same formula for the lens. This is the thin lens formula, where x is the thickness of the lens, r is a position from the center of the lens radially outwards, r is the size of the lens, it's the actual physical size of the lens, and f is the focal length. So I can get the same answer in 2 completely different ways. I can get this answer from Fermat's principle, which is a particle or ray view of light, and I can get this answer from the wave picture of light, and the two are completely consistent. So, no resolution to the question of particle or wave there. I get the same answer both ways around. The next great development of electricity and magnetism was Maxwell. And Maxwell unified electricity and magnetism in 1862. And he showed that electricity and magnetism were related phenomena, and that electromagnetic waves, light, radio waves, were just starting to be discovered around that time, were really propagating electromagnetic waves where the electric field and the magnetic field are perpendicular to one another, and these waves that you can see, so there is one of these waves, is propagating like a water wave in this direction. And as the electric field propagates in this direction with the electric field vertically upwards, the magnetic field propagates in exactly the same direction, but perpendicular. Now we already know that light is an electromagnetic phenomenon, and so this is the framework in which we really need to discuss what is light, really. Now, if we consider diffraction from a pinhole, as we were discussing just before, if instead of having a coin blocking out the light, if instead I have a big screen with a hole in it, then I can solve exactly the same equations and show that the intensity distribution makes exactly the same sort of pattern as we saw with the spot of Arago. That is that you can see this big maximum, and you can see these subsidiary little rings. These are the little rings that you can see in the diffraction pattern around a circular obstacle. And in fact, there's a principle called Barbonet's principle, which says that the presence of something is exactly the same as the absence of something. And so the diffraction pattern that you get from a coin being illuminated by light is exactly the same as the diffraction pattern you get from the screen with a hole in it that's the same size as the coin. And if you were to look at the diffraction pattern from this pinhole, there is the bright maximum right in the center of the diffraction pattern, which actually generates the spot of Arago. And as you get closer and closer to the center, it starts to spread out and distribute its intensity. If you got very close, then actually you wouldn't see a bright spot at all. Now, here's an experiment I performed earlier. This is an experiment that my group performed at the Australian synchrotron, and it's a relatively simple experiment in which we illuminate a pinhole with 900 electrons or photons and collect the diffraction pattern. This black thing you can see here is merely to protect the detector. Because X-ray diffraction is rather weak, most of the light just basically goes straight through the pinhole and would actually just bore a hole through the detector if we let it. And so behind here, right at the tip here, is actually probably about as big as the green spot you can see. That's the original beam that's coming from the synchrotron. And then all of this is the light which has hit the edges and been scattered upwards. And this set of slides actually tells you a great deal about the particle-wave duality of light. Here is 1 second exposure. of pinhole. And here is another one. You can see it's slightly different. It's got the same sort of general features, but you can see way out here, you just have these individual, rather noisy signals, which represent small numbers of X-ray photons which have been scattered. And in fact, if you do this experiment more carefully, you can measure individual photons, one photon at a time. You either see a little flash or you don't see a flash in the detector. And if you get another one, you can see it looks like that. It's kind of similar to the last one and similar to the first one, but a little different. And if I do this enough times, 500 times it turns out with 1 second exposures, and I add them all up, then what I see is actually the true diffraction pattern of this pinhole, which if you look closely has all of these rings. These are the rings that I showed you earlier, the ones that I expect to see from mathematics. And all of this cloudy stuff here is actually photons scattering off the ragged edge of the pinhole. It's more difficult than you could possibly imagine to make a really smooth pinhole. You think it would be the simplest thing in the world, but light is very small and pinholes are comparatively really big. And so all of these streaky things that you can see coming up here is light scattering off the daggy bits on the inside of the pinhole. But you can see that this is like a wave. This is now a continuous wave-like representation of diffraction, whereas back here, I've got a collection of individual signals, which are particle-like. Same experiment, different information. Particle-like information up here, individual strikes of light at large angles. Add it all up, wave-like, same experiment. So this experiment, I'm basically seeing the wave-like and particle-like behavior of light simultaneously. And these days, it's actually possible to do the experiment in which I shoot one photon of light at a time through the pinhole. One photon of light goes through the pinhole and goes to the detector and makes one and only one splash on the screen. And then I do it again, I do it again, I do it again, I do it again, I do it again. A group in Japan did it over and over and over again. And then they looked, you know, what you see if you make a movie and you accumulate the movie as dot, 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 splash, 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 back to splash, and you end up with that. It looks like a wave, but actually behaves like a particle. X-ray diffraction is very weak. We do not record the expected diffraction pattern from wave theory with short exposures. I don't get that unless I sum up lots and lots of experiments. I actually get that. I clearly see individual events. I clearly see where the light arrives. I see single detector pixel events, and they change from shot to shot. If I accumulate enough images, we obtain the expected pattern, that smooth pattern of concentric rings. But light arrives at the detector in discrete packets, as if it's a particle. It is not a wave in the classical sense of water. So light is not a wave. It seems to be a particle, but we have to qualify exactly what we mean. What actually is true is that the diffraction pattern of wave theory determines the probability that a light particle will arrive at a particular point. When I perform the experiment one photon at a time, and the photon has to go somewhere, but it goes to that particular point on the detector with a probability which is the square of the wave that I would calculate. But nevertheless, it's a particle. It goes from the source through the aperture to the detector, and it's just recorded as a single event. I don't get a very faint representation of the entire wave. I just get one spot. And what happens is that in an experiment, I never perform an experiment just with one photon because I wouldn't get much information. I perform experiments with 10 to the 12 photons, 10 to the 13 photons actually for that one. And so I'm actually accumulating information in short bursts over long periods of time, and I build up a pattern which is characteristic of a wave, but actually the thing is not traveling like a wave. That wave is actually the probability of a particle reaching the detector at a particular point. So light is not a classical particle because it can't account for diffraction or interference or any of those phenomena, though I can explain refraction and reflection and the formation of shadows. But it doesn't explain diffraction or interference. But it's also not true to say that it's a classical wave, because we observe that light is detected photon by photon when the light source is very weak. Diffraction patterns are actually a measure of probability. And so the correct description of light and electrons and protons and neutrons and all particles which you know are covered by quantum mechanics, or you will one day know are covered by quantum mechanics, so-called quantum particles, are really described by probability and statistics. And that is the truth of the matter. The photoelectric effect. Now, the energy of photons, energy of electrons ejected from a metal surface depends on Planck's constant and depends on the frequency of the radiation which is ejected. When you know the experiment, you shine light on a particular sort of metal, usually sodium or lithium or potassium, and the electrons are ejected from the surface. They cause the current to flow. You can measure that current, and you can actually stop the electrons from being ejected from the surface by applying a voltage or an electric field. And you can work out how much energy the electrons have by providing just enough electric field or just enough energy to stop them from causing a current. And this experiment was proposed in 1905, and it actually took a long time to do it properly. It's a very difficult experiment to do, actually, quantitatively. And when it was, ultimately, I think by Millikan in 1918 or 1919, this was the reason that Einstein won the Nobel Prize in 1921, was actually the photoelectric effect and the experimental demonstration that the energy which is transferred by light to materials is transferred in packets. And the amount of energy is transferred with an amount h nu, or h bar omega. So Einstein interpreted this photoelectric effect as indicating that light behaves like a particle, that it carries a certain amount of energy. That energy is h nu. An atom has to absorb or emit an entire photon. It's all or nothing. It can't nibble at the light. It has to gobble it all up or spit it all out. It can't just kind of nibble at the edges. And for that single discovery, Einstein received the Nobel Prize in Physics in 1921 for the photoelectric effect, not as many people imagine for the theory of relativity or Brownian motion. Einstein himself said there are now two theories of light, both indispensable. It's just more convenient sometimes to think of light as a wave or as a particle for the purposes of calculating its properties. And one must admit today, which is 1924, in spite of 20 years of tremendous effort, 20 years ago was 1904, which is basically 1905, which is when he wrote his paper on the photoelectric effect. A tremendous amount of effort. There are no logical connections between them. So in 1924, basically there were particles and there were light, and people just kind of juggled the idea. And this kind of juggling still pervades a lot of thinking, a lot of discussion. But we do have a more sophisticated view of light these days, of quantum particles generally. At the end of his life, in 1954, Einstein said, all these 50 years ago, it's 1904 obviously, all these 50 years of conscious brooding, it absorbed his life, absorbed his thoughts for 50 years, have brought me no nearer to answer the question, what are light quanta? So it's not a simple question to answer. All we can really tell you is how light behaves. These days, every Tom, Dick and Harry thinks he knows all about it, but he is mistaken. And as you know, one of the Harrys of the world, I think, you know, I know better than to say I know all about it, but I do know how it behaves. And this is all we know about light. We know how it behaves, and we know how to describe it in a logically consistent fashion. But it's not possible to say it's a particle or a wave in the classical sense of the word. It behaves more like a particle, but with a proviso. And I shall now tell you that proviso. Well, actually, I will in a moment. This is just funny. William Henry Bragg, who was born in Australia, born in Adelaide actually, won the Nobel Prize in 1915. He rather humorously said that physicists use the wave theories on Mondays, Wednesdays, and Fridays, and the particle theory on Tuesdays, Saturdays, and Thursdays. And obviously there was no physics done on Sundays.
Well, you rested, did you?
Well, one rests, does other things. And that was a perfectly respectable position to take 100 years ago. You see, light forms part of a much more sophisticated theory, and that more sophisticated theory is the standard model of particle physics. Light is a photon, and that is light. It's the carrier of a force. The photon is the carrier of the electromagnetic force. Light is a propagating electromagnetic field, and the photon is actually the thing that transmits the magnetic and electric forces between particles. And in that sense, it has the same status as the W and Z bosons, the Higgs boson, and leptons and quarks. It's basically one of the elementary particles of modern physics. And so we regard it as a particle, but with a proviso. And that is that all of these particles, including the photon, are described by quantum physics. And quantum physics is really based on probability amplitudes. The probability amplitude is the property that the particle carries with it as it travels through space. And how it travels through space is really the interesting question. Now, there is a theory, it's a very fancy name. The theory of electricity and magnetism is called QED, or quantum electrodynamics. And the behavior of electrons and positrons and photons are all described by the theory of quantum electrodynamics. It's the most precisely tested of all the physical theories, and it's a theory of probability, ultimately. It's a theory of probability, not of particles or waves, it's a theory of probability. And actually, although it's a very fancy thing, and we only teach it to you in masters, and even then, you know, it takes you even longer than that to really master it. There's only really 3 basic rules of QED. A photon travels from A to B along every possible path. Every path is associated with a complex number, a factor e to the I theta, and this is called a probability amplitude. So every possible way that a particle can get from here to there, that way, this way, every possible way, round in a circle, everything counts. But in doing so, the paths that go in the straightest line count the most, generally speaking. An electron or a positron travels from A to B also along every possible path, and every path of the electron or positron is associated with a similar probability amplitude. And then the third rule says that electrons or positrons interact with photons either by entirely absorbing the photon or entirely emitting it. They are the 3 rules of this fancy theory of quantum electrodynamics. There are no other rules, but there's a lot of maths. And that is the way that we actually visualize how light works, how light interacts with matter, how electrons are bound to nuclei, how they form atoms, how atoms form molecules. That is the logical structure. Way deep down, those 3 rules. They're the basis of chemistry, and ultimately of biochemistry. They're the basis on which the extended rules of particle theory and particle physics are based. They all stem from this. And you can read about it. Actually, you can read about it from the guy who invented it. Richard Feynman actually wrote a very accessible book, and if you're interested in this, you can easily read it yourself. QED, the strange theory of light and matter. It doesn't have any equations in it. It's entirely non-technical, and it goes into much more detail than I can do in an hour about the nature of light and quantum mechanics and the connection between the two. It's quite humorous. Feynman won the Nobel Prize in 1965 for the theory of quantum electrodynamics, which is the theory of light. And insofar as we understand light, and whether it's a particle or wave, we understand it through that theory. So what is it all about? We can only ask the question, what is the probability that a photon will go from A to B? So there is A, and there is B, and I want to know how it gets from A to B. Well, in the classical theory, it goes in a straight line. That's the ray theory. But we know the ray theory doesn't describe everything that we know about light. What Feynman did, and it was a tremendous leap of imagination, is he said, well, I prefer that I didn't have any preference about this. I prefer that the light go from A to B by every possible route, and I just have to have some way of weighting this route and that route, and this route with a squiggle in it, and the route that goes like that and goes over there, and every other one. Light in principle should be allowed to go any way that it wants, every way that it wants. add up something that's associated with each one of these paths, which is like a wave, add up all the probability amplitudes for every one of those paths, and then square it. So each one of these paths is like A plus B squared. A is a number which is associated with that path, and B is a number which is associated perhaps with that path. And what I do is I break up the paths between A and B in every possible path, add up all of the numbers associated with those paths, square it, and then get the probability of going from A to B. Each one of those paths then has this probability amplitude, which we call phi I. I sum up all of those numbers, and then the probability of going from A to B is the square of those numbers. So the particle carries this information with it. It goes from A to B by some crazy route, and it carries with it this number, puts it in its pocket, and says, I went this way, and I have this number, I went the other way, I have another number. It adds up all of the numbers, it squares it, and that's the probability of going from A to B.
Professor Quiney, what about Newton's laws of motion applying to the particle? So Newton's first law would tend to go in a straight line and that's active on the external.
Yeah, well, in fact, Feynman came up with that as well. In fact, Feynman based his theory of particles, electrons, protons, and so on. Not so much on Newton's laws, but on Lagrange's laws, which are a generalization of Newton's laws. And so Newton's laws are largely based on the idea of energy and the Hamiltonian. Kinetic energy plus potential energy is the total energy. Lagrange's theory of mechanics, classical theory of mechanics, is actually the difference between kinetic energy and potential energy. And that difference actually contributes to that factor, this factor of phase in classical mechanics. Feynman was the one who actually worked out how to calculate that phase for electrons, protons, solid particles, particles with mass. But the rule is still the same. They travel from A to B along every possible path, and then you use Newton's laws, actually Lagrange's laws of mechanics, to calculate the probability amplitude, which you derive actually from classical mechanics. You sum them all up, and then you square them. It's the same theory, actually, but it does actually come from classical mechanics. Not so much from Newton's laws, but it comes from Lagrangian mechanics. The quantum theory, this crazy idea about summing up all the parts, gives you exactly the same answer as you would get from the wave theory, exactly the same. And in fact, there was quantum mechanics before Feynman, and all Feynman did was he restructured the logical picture of light in quantum mechanics in a new way, in this kind of way which describes particles and paths. As I said before, the same approach applies equally well to electrons or positrons or protons or neutrons or any quantum particle. Indeed, you can fire buckyballs at Young's double slits, and you can actually form a diffraction pattern from buckyballs, entire molecules being shot through as quantum particles. The buckyballs have a probability amplitude, and they sum up and actually give diffraction spots on the screen. All of what I've told you today is not just the law of light, it's the law of everything. It's the law of quantum mechanics. All quantum systems behave in this way. They are particles, they are associated with probability amplitudes. You sum up all of the amplitudes for everything the particle is possible, is capable of doing, and then when you square it, that gives you the probability of a particular event. The maths is hard, the idea is actually relatively easy. And this is actually the foundation of the understanding of everything. Particles, subatomic particles, the standard model of particle physics, they all work in essentially exactly the same way except for gravity. For some reason, which we don't currently know, gravity works in a completely different way. And no doubt someone else will come and tell you about the underlying laws of gravity. So in summary, the behavior of light has guided physics for more than 400 years. Is that roughly right?
Oh, this is perfect.
There you go. The behavior of light has guided physics for more than 400 years, and it's been the guiding light for everything else. We understood light, and light helped us understand electrons, and electrons helped us understand subatomic particles, and it led to the standard model, which led us to be able to understand electricity and magnetism, which allowed us to understand how atoms form into molecules, and molecules into solids, and molecules into biomolecules, and biomolecules into life. Basically, it all comes ultimately from this one idea. It's quite remarkable, but it came from light. If there's no diffraction, then usually ray models are perfectly okay. If all you're interested in is lenses and mirrors, a ray model for practical purposes is usually okay. If you've got diffraction, then usually you need a wave-like behavior, but we do observe individual particles of light arriving at a detector if the source is weak. And I showed you those noisy diffraction patterns from my group. We still see diffraction patterns if they're recorded one light particle at a time. I can build that wavy diffraction pattern by throwing one photon at a time at an aperture, collecting where it goes, and it will be probabilistically distributed. And if I sum up all those experiments, I will get the wavelength behavior. And indeed, that experiment has now been done. The photoelectric effect suggests that energy is quantized, and the energy of each of these quanta is h nu. Light is described by probabilities rather than waves or classical trajectories. Is it a particle or a wave? Well, it's a particle associated with probability. I think that's probably the most accurate description that I could give you. For practical calculations, you can treat it as a wave or treat it as a particle depending on the situation. But the unifying vision is that it's a particle which carries with it information about its probability distribution. If we have lots of photons, we observe classical behavior. So if we have lots of photons, we can observe this wave-like diffraction. If I have one photon, I see a spot. And at a fundamental level, the behavior of electrons and other particles are described by the same rules as photons. Ultimately, what I've told you is the kind of the foundation of modern physics, actually, apart from gravity. It's a quantum world, and the quantum world is pervasive. Thank you very much.
Wow, I hate people who finish their lectures on perfect time. But thank you very much. Yeah, perfect. All right, we've got time for some questions. I'm also giving the guys up in Wodonga a chance to actually get their questions. Go around the room quickly. Slowly.
I have a question.
You have a
I
question?
have a question for the students sitting up here without their teachers.
Yeah?
I suggest that tomorrow or this week, when you have your next lecture or class in physics, you ask the teacher something about this particle wave duality. You've just heard and seen some references to some of the most interesting bits of physics. And I'll be interested to hear what your teachers can confirm or otherwise about what they know about this. Sorry.
All right, well, thank you, Max. So that was a statement rather than a question. Yeah, okay, Frank, there's a question. Frank, just so the kids up there feel...
Maybe it's not entirely relevant, but when an electron and a positron meet, suddenly they just turn into pure light. Yeah. Is that contained within this framework?
That's really contained within the theory of special relativity. That E equals mc squared. If I have an electron and they're slow electrons, so I just ignore the fact that I have kinetic energy, the mass of the electron, mass of the positron are the same, and the energy on this scale is of the order of 0.5 MeV. So the energy of the two of them when you collide is about 1 MeV. And what happens is that if I have an electron and a positron come here, then actually, yes, the quantum theory of quantum electrodynamics says that the energy has to be conserved, and the two particles, charged particles, interact either by the complete absorption of a photon or the emission of a photon. Well, what actually happens is that in this particular case, two photons for reasons of symmetry.
Actually, we could ask, oh yeah, the students will get to learn that at some point.
Yeah. So this is an electron, and this is a positron. That comes under my three rules. My three rules that I have charged particles, electrons, and positrons. I have photons, and the charged particles interact with photons, either by the complete absorption of a photon or the emission of a photon. So it's that rule. It comes under rule 3.
We have no questions so far from Wodonga, Harry, so it must be extremely clear up there. Yeah. Anyone else with a quick question? Anyone else with a slow question? Harry, what about these, you read sometimes, okay, we've heard about the opera experiment, faster the speed of light. What about the other people who claim they can make things invisible, you know, like cloaks and all these types of things? Are they real? New metals,
Yeah, metal material.
For our submarines or whatever.
Metal material. Well, the presentation I gave today was really about light involving ordinary materials, glass, water, air, and so on. And under those circumstances, the refractive index is an integer, well, it's a number bigger than 1. And under those circumstances, you disregard the fact that light can be absorbed. The light is merely bent through the material. But light can also be absorbed by a material, and it can be bent by a material. And so actually the refractive index is, generally speaking, not just a real number, it also has a factor that is proportional to I, its absorption characteristic. Now, it turns out that if you can get a material which behaves in a particular way, you can actually get it to bend the wrong way, the so-called negative refractive index materials. But these are not materials in the usual sense of the word. They're not solids like glass or air or water. They're actually little antennas. And these little antennas actually absorb the light and then re-emit the light with a phase relationship which is determined by the structure of the antennas. These antennas can be made these days because we have the ability of nanofabrication, the ability to actually make very, very thin but very precise metallic objects either by depositing ions on a surface or by chipping away a metal surface and revealing an insulating substrate. And so if you get a piece of silicon or some kind of insulator, you cover it with a metal and you chip away to make structures that typically look like this. When the light comes in, it actually causes the electrons, because I showed you that light is an electric field. It actually makes the electrons, the electric field and the radiation causes the electrons to go up and down. And so in one instant, you're going to have a build-up of charge here, which could be negative. And because the electrons have run from the bottom surface, then they're going to end up being positive at the other end. If I have a material that's like that, and it's oscillating positive, negative, negative, positive, that's actually a radiator. That's how you actually produce radiation. And so this material will absorb the light and then re-radiate the light, possibly at a different frequency and possibly in a different direction. And by tinkering about with the geometry of these structures, and by the materials that they're made out of, and in particular the dimensions of these wings here, you can actually tailor-make the radiation that comes off to the extent that you can cause radiation to actually hug around the surface of a material. It's used in stealth technologies. It's used for actually making radio waves instead of radio waves bouncing back, making radio waves actually pass around the surface of material and be reflected backwards away from the source so that the aircraft or the ship is invisible to radiation. But it really comes down to manipulating the response of metals to the electric field and radiation, and then to re-radiate that signal in a different direction, which behaves collectively. And actually, there are lots of these things. It's not a single one. There are thousands and thousands of these distributed on a plane. You can make the material actually bend light the wrong way.
And therefore make it
cloaked. And cloaked, exactly. So basically, instead of scattering light that way, scatter the light inwards.
We have a question from Tyson, and he says, or he or she, but I'm guessing he, why haven't Einstein's questions ever been answered? And in particular, what are light poncha or something? Yeah, so that's the question. Yeah.
Well, it's because Einstein really struggled to come up with an accessible and classical explanation for physics and the concept of what he called causality. Einstein was particularly concerned about trying to understand the nature of interactions between particles and what he called the spooky interaction at a distance. The quantum particles have some very exotic properties that I haven't gone into today, but what Einstein really wanted was an explanation about how the familiar classical world and the idea that everything is cause and effect related to the quantum world, in which there are more important principles, largely to do with symmetry. That's an example of symmetry. If I have two photons that are produced in a particular way, these two photons aren't just any two photons. These two photons will propagate with their electric fields, actually coupled together. So if this electric field is that way, then this electric field is the opposite way. And it will do that forever. These two photons will, in principle, propagate to infinity forever. And if I measure the electric field on this photon, I will immediately know the behavior of this photon because these two photons are coupled together. That spooky action at a distance, actually why it happens, is not such an easy thing to understand.
But yet there are people using this.
Oh, it's used all the time. And in fact, this and optical photons, these are X-ray photons, but making optical photons and coupling together their properties is one of the base technologies of quantum cryptography. Basically, secret communications and being able to have secure communications that can't be intercepted. Simply the fact that anyone eavesdrops on a system in which you know you have two photons, and those two photons or two particles, two electrons, or whatever, have a strict relationship with one another. If someone eavesdropped, then they'll give the game away because the signal will be propagated into the other photon.
And do you believe that?
Well, what I believe possibly shouldn't be shared. Just in case the NSA is listening.
Okay, and Tyson, I'm really sorry. So Tyson's a she. All right, guys. There's okay. Question up the back.
Was trouble with field?
Fields.
Okay, let me just repeat the question so the kids up there hear. So, was Einstein trouble with the concept of fields?
Yeah.
Okay. Yeah.
Not inordinately, because Einstein's general theory of relativity is field theory, classical field theory. So he wasn't against the idea of fields per se.
Now, did you guys understand what that question really meant in the front row? So, do you know what a field is? It's not a paddock, right? So it's not that, right? But okay, you asked some great questions that week. Who's played with magnets? Everyone, right? And can you feel the magnetism between two magnets and whatever? Well, what carries that magnetism?
Does it occur between 2 points, or is it a property of the space between?
Yeah.
And the truth is that it's both.
Yeah. And in physics, the answer is always going to be it's both, neither, or the other, whichever is convenient.
There are two ways of looking at, say, Coulomb's law. Now, you probably know Coulomb's law at school. If I have 2 point charges, then the force between them varies inversely as the distance between. So if I have point charge 1 and point charge 2, which perversely I call A and B, and they're separated by distance r, then you know the force is proportional to 1 over r squared. So you might imagine, well, something is happening in a straight line between these two particles, that something is a property of the distance between them. But on the other hand, this charge here actually sets up what we call an electric field. This is called electric field of A. And this actually also sets up an electric field, which is the electric field of B. And it's actually, from another point of view, those two electric fields interacting with one another that causes the attraction or repulsion of charged particles. Because the interaction between these electric fields actually generates an energy density. There is energy in this region of space, in a vacuum, where apparently there is nothing. And all I have are 2 point charges, point charge A and point charge B. This is generating electric field. This is generating electric field. This electric field is over there. It's not between the line between the particles. If I take this particle away, it's still making an electric field. I bring this particle up, it's making an electric field. From a point of view, I can show mathematically, well, I won't do it now because it's getting late now. I can show actually the force between these two is either Coulomb's law, or it's the sum of all of the energy distributed through all of space produced by that electric field interacting with that electric field. And those two are completely equivalent. One is the laws of Maxwell, the ideas of fields, or Maxwell and Faraday actually. Faraday was the one who really introduced the idea of a field. And the other is the idea of potentials, an action at a distance, and what we call the potentials of Leonard and Pickett.
Which is the general standard model. And at the same time, the standard model will say that the photon is carrying that.
Yeah, and the photon is carrying it because it's distributed. The photon goes between these 2 points by every path. Every path, not straight line, every path.
And where's the photon?
All right, we're gonna, okay.
Oh,
We're
it's in the field.
Oh, it's everywhere.
It's in the field. Yeah.
Okay, oh, wow, fantastic. Nice and loud. Yell your question out so we'll see whether these guys can hear it. Harry, can you repeat the question? I'll repeat the question. If the photon can travel through many paths, how can we calculate it?
Oh.
And Harry did mention in the lectures, but let's remind you again. Yeah.
But you sum them up. Let's just say it wants to go from A to B. Let's just say it goes by that path. I can calculate it simply by going in a series of little straight lines. And each one of these straight line segments changes this phase, this probability amplitude, in a way that I can calculate. And in fact, to within a constant, for light, so not for electrons, but for light, the change in the probability amplitude is actually that number. It's make it even more definite.
This will be on the VCE exam.
So, and t is the time it takes to go from there to there. How long does it take? Well, it travels at the speed of light because it's light, right? And so you divide by the speed of light, it's in meters per second. And so you work out the time it takes to travel that particular distance. And so I break up this path into every little path, and I work out this contribution along each one of these little paths, and then I add them up, and that will be path number one, path A.
Do they then cancel out with another path?
Yeah, and so it turns out that when you add up all of these paths, the only ones that really count in the final analysis
are straight across.
And a small number either side. So you sum them all up, but the only ones that really survive the trek are the straight line ones, or the ones just slightly either side of the straight line. And then you formally sum up everything else, but everything else essentially cancels out, simply because it wriggles back and forth above and below zero, simply because it's sine of omega t. So only the paths that go more or less in the same direction as the straight line add constructively, and all of the other ones, well, they just add up to zero. And so there are maths. Come and see me in 6 years' time.
All right, and Tyson, I'm just going to pick up your last question here. I've got it here, and I'll read it out, but we won't answer it, I think.
Okay.
It's in chemistry with NMR, which stands for nuclear magnetic resonance. We have radio waves interacting with nuclei, affecting the nuclear spin. Is there a simple way to explain the chemical shift?
Yes, there is.
Oh, there's a simple way. Okay, Tyson, you get this answer right.
Yes, there is. Nuclear spin. Essentially, when you do this experiment in chemistry, you have a nuclear spin which you know can either be up or down. And it's either up or down.
I'm just going to explain for those in the room, NMR, or we're also MRI machines in hospitals, magnetic resonance images. Yeah.
If you get a system with nuclear spin and you put it in a strong magnetic field, then without the magnetic field, spin up and spin down has exactly the same energy. If you put it in a strong magnetic field, it actually splits the energy levels by an amount delta E. But delta E is equal to h nu, where nu is the frequency of the light. And what is the frequency that you use for NMR? Well, it's radio waves. The NMR experiment is a little radio wave generator, which is tuned to exactly match this energy difference. And so your question is, how can I explain the chemical shift? Well, the way I've explained it here is I've ignored the fact that this nucleus is surrounded by electrons. If I embed my nucleus, so here is my nucleus, and here is my molecule. Okay, it's got atoms and all stuff, but basically it's covered with electrons. So I imagine I've got electrons going around like this, and I apply a magnetic field. The fact that I've got electrons, they also interact with the magnetic field and they change the value of the magnetic field at the position of the nucleus, simply because the electrons themselves have their own magnetic moment and they also interact with the magnetic field that you apply. And so this difference here, delta E, is a function both of the chemical environment, whether I've got a methyl group or an alkyl group, but also the applied magnetic field. It depends on the magnetic field strength and on chemistry, on the electrons which are swirling around. And different chemistry tunes up the electric field, tunes up the energy differences in small ways. And so you can actually get very small energy differences and tune them up with different radio waves. And so it's a very sensitive test to the chemical environment. And you know that different chemical environments are very sensitive to whether it's a methyl group or an alkyl group or whatever.
Harry, I threw it to you because I know Harry spent time as spends time as a theoretical chemist as well as physicist. What a journey. Have you guys had a good lecture tonight? Can you give him a big round of applause? Max wants me to remind you that in 2 weeks' time, also the people up in Wodonga, if I do that, I'm in on camera, so I'll just stand down here. In 2 weeks' time, we've got Christian Reichardt taking us on a journey of astrophysics, I think, or somewhere. Yeah.
I think the lecture is going to be interesting. You heard lectures from our department of astronomy.
Yeah.
This is the new guy.
Yeah.
It's interesting.
Yeah. So
those of you that are here without your teachers,
yeah,
that's most of you, you might mention to them that you had a good lecture tonight, and they would have benefited significantly. They've got a chance to make it up in 2 weeks' time.
Max isn't backward in
And
coming.
I'll be sending you another.
Yeah, Max will be smacking anyone who doesn't come. Any teachers who don't come from now. Okay, guys. So Wodonga, Julie, and Michael, and everyone else. Thanks very much. Very well. Thank you. Come down and say hello to Harry now. Yeah, come on, quickly. Yeah, these guys are one of them. No. Sorry. Just realized. Yeah. Let's do that. Let me shut down 3 minutes of the meeting. No? Yes. Well, there we go. This is live. If I do this now.